Hi, I am Dongheui Lee from Technical University of Munich and German Aerospace Center, DRR. My talk is a part of the Humanoids 2020 conference workshop on floating-based robots in manufacturing and logistic operations, opportunities and challenges. So today I would like to talk about how robot learning could enhance robot programming for manufacturing. During the last decades, we have pushed industrial robotics from this conventional heavy robots behind the cage towards to the more lightweight collaborative robots which can share the workspace with the human partners. And conventional robots are featured with high precision and high repeatability and also high payload. But of course, the safety is not ensured. So we look more towards now lightweight robots using more compliance control there, which allows us to physical interacting with the human partners. And along to this, also robot programming has become changed. Current trend is using more smart pad, like tablet-like intuitive interfaces, and people use a lot so-called direct teaching, or some people call program by demonstrations or kinesthetic teaching. And I say now this will become even empowered if we can combine it with robot learning from demonstrations. So my talk will be about this. So in order to answer, how does robot learning enhance robot programming? My talk has 4 parts as shown in this Outlook slide. So let's start with the first part. What is the basics? The robot learning by kinesthetic teaching. So you can see direct teaching has been used like at the beginning, key pose memory. So human user moves the robot in a certain special important pose and then recording that pose. And then reproduce the robot's behavior by just linear motion in between the key poses. And this can have any generalization capability to the new situations. And in the earlier work of learning from the demonstrations, we could teach the robot some trajectories, like nonlinear trajectories. And also it could have more generalization behavior, like dynamic movement primitives. It can reach to a slightly new goal positions. And more recently, we could also teach or refining already learned motion trajectories using incremental learning approaches and also using more active compliance control. And this was what we proposed about 10 years ago. And this was the first work which can do the direct teaching while robot is executing already learned tasks. So we know that kinesthetic teaching has been used a lot in the industry setting, and it is also suitable. But often you also realize that kinesthetic teaching is often used only to teach one task, let's say end effector motions. But what if we want to teach multiple tasks? So let's imagine I want to teach a robot some end effector behavior, but also another body parts, let's say elbow. In this case, what we proposed is we first teach end effector motion, and while robot is executing end effector behavior, learned one, then we show another ones on top of it. So we basically try to augment a new skill on top of previously learned skill. And we formulate this as a prioritized multitask problems between already learned task and currently teaching target task, which is shown as a TIC, interaction basically. In this particular example of teaching two tasks, we can define three possible sets of the prioritized tasks. First set is only having end effector tasks. And second task, we add this new teaching target as a secondary task when humans start to pushing that, when humans start to insert some forces weakly. And human force insertion becomes stronger, then this task becomes higher tasks than the end effector task. Then we calculate the inverse kinematic solution for each set of the prior tasks. And we sum it up with weights. And this weight, the sum of the weights are weight is 1, and these are governed by the linear dynamic system. So when we switch it from one set to the another set, it's slowly, smoothly changing from here to here using this W. So in this way, we can easily, anytime, add or delete or change the prior task. So add another task or delete another task or change the priority of the between the tasks. So here is an example of the same thing. So first we teach a robot end effector behavior first. And now it learned the end effector behavior. And then the user shows also elbow motions because in the now new workspace, there is another object in the workspace. So in order to avoid any collision in a new situation, we have to teach the elbow motions. And then we can learn both tasks simultaneously. And this multiple task teaching is very useful also for the humanoid robots. Usually humanoid robots have multiple tasks at the same time. And also it has the high degrees of the freedom as well. So in this particular example, we taught a humanoid robot, via a humanoid robot Toro, how to do a bimanual lifting task. And it can also reproduce the task using the same box, or it can generalize this lifting task to the much smaller object box as well. In this work, actually, we particularly focused on these disturbances, which can be inserted to the robot because of the direct teaching. So this kinesthetic teaching, direct teaching force can disturb the balancing of the bipedal robot and how to compensate that. And that work has been published some time ago, so I was 2013, so you can check this out as well. So let's go back to our current trend of the robot programming of industrial robots. So we started, we use such kind of a tablet to program the robots, and often you can sequencing multiple skills one after the other. But what if this sequencing is not really fixed all the time, or it's not really a sequence, but it has a multiple paths, like such thing. Depending on your conditions, you have to do sometimes this behavior or the other behavior. So we will deal with now how to teach the conditional tasks, which requires conditional reasoning. So here, this is our very first approach. So we actually, at the beginning, we just showed all the possible solutions here. And just to look at them as the unsupervised clustering approaches. So you can cluster the similar trajectories or similar demonstration into one skill, another similar ones as one. And when robot is executing, when you don't know where it is, then you just execute either one of it. And where the branches happens, then if you choose the wrong skills, then maybe you see some deviation from your expected trajectories, or some behaviors you was expected sensory observation, you will get it. Then you will switch it to the another strategy. That is our solution. So let's see a robotic experiment. So in this case, we taught robots how to do the milk carton sorting. So here you see the human demonstration. He shows now when milk carton is empty, put that into the right-hand side of the bin. And when it is full, put it on to the left side. And then it does unsupervised clustering, and then learned two types of possible strategy. And when it is executing, you can hardly see that before it acts on it, but this time it happened to choose the full, and then it collected the, it was correct, so it went to this. But here now it started with full, but when it lifted the milk box, it realized no, it is empty. So it switches now to the empty carton sorting strategy. Basically, what you see is you expected what is expected false information, and it's the variability. But when you measured in real time, you see some differences, then you switch it to the different solutions. So here is another example of the sorting. It's not only the binary, but now it has three categories. So these are the objects arriving to the picking location on the conveyor belt. So when it comes, profile comes, then you put it here. When empty box comes, put it into the middle. When full box comes, most the inner side. And again, similarly, human demonstrator just demonstrates without explaining much. And then robot uses its proprioceptive sensor information to cluster what are the most closest demonstrations are together, and it learns different categories of the skills. Now full box comes and you want to put it in here. And now when just the profile comes, he just shows now pick and place to this location. Again, all done without any labels. Now, this is the robot execution stage. It started with the empty box. It was luckily correct, so it did correct sorting. And now, when the full box comes, but it started with the empty box because it doesn't have any vision sensors. And when it lifted, it detects something is wrong. So it switched to the now full box strategy. Again, no vision, you just go to the picking place of one of these skills. Empty, oh, I didn't lift it up. Okay, I will switch to the full box strategy. Oh, again, it doesn't work. So now I go to the profile strategy and then sort it correctly. So here you can see also how this distances from distances of the current measured data to the expected sensory values. And when these sensor values are becoming higher, then you switch it to the new strategy. So I explained here how to deal with the conditional tasks. Basically, we use the anomaly detection to switch between the existing skill strategies, basically. But in fact, we thought anomaly detection can be used in a more intelligent manner. So imagine you only learned something long time ago, but now of course situation has been changed. Now you see a differences and then you found some anomaly there, and then you can use this anomaly to extend your current existing skills. Maybe your previous demonstration or teaching that your teacher didn't show all the possibility in the world. So you can use anomaly to expand your knowledge. And this fits well to the continual learning, and also because the U triggers when to learn again. So this corresponding to the more active learning. So here is a task. The task is very simple. When you have such an object, just place into the target location. But when an object is 90 degrees rotated, but you have to place again in a correct way. So you have to rotate this object and place it. So this is a simple task, but you can see there might be some similarities between two, but then you see the some reasoning parts and there is not happens, then you have to go either different ways. So let's see in this case, first the human teacher only showed the first solutions. So okay, just pick and place exactly same orientation manner. Now in the environment, object has been rotated 90 degrees. And when robot executes what it has been learned before, it will not able to lifting it. And when it has something different, measure the values compared to your expectation, and then you can see this variation, the deviation from the expected one becomes larger than the variability you expected. That it says, oh yeah, there is an anomaly. Then what should I do? So it reports this anomaly to the human user. Help me. There is a false error. I don't know what to do. What do you want me to do? So you can have choices, like either you say, okay, no, this is existing skill, so just refine your current skill. Or it can say, actually, it is a new skill, so I will give you a new solution for this. So in case people choose refine existing skill, then you can see like this. So your expectation was here and your measure is here, and this measurement goes into the learning, right? So you can see it has updated mean trajectory, and also it has now larger variability. When human says, yes, it is a new skill, you have to learn something new from here, then I will show you how to deal with this situation. So human says, okay, from here, pick and rotate and place. And this demonstration has been shown. Then you can see previous demonstration was here. And when there was this anomaly has been detected, then you split up this previous trajectory into two, and then you connect with the new demonstration here. So you see the branches in the middle where the anomaly happens. And this is basically where conditional reasoning really happens. So with this, now you can see it tries to lift it, and then you realize, oh no, this is different angle. So it tried again, and then it rotated. So we keep using anomaly detection during the execution and also to do the more active learning as well. So I explained our very first work, basically showing the multiple strategies and clustering them, and then using the anomaly detection during the execution. And then this anomaly detection switches to the different solutions, basically. But on the other hand, the last shown approach is we call it collaborative incremental programming approaches. So it also allows our task representation to have some branches, right? And also, whenever we detect anomaly, it can also trigger now. What is it? I want to have a new data, how to handle this. So it triggers active data acquisition, in contrast to the previous work, which only gets data passively from the users, right? And this allows more continuous, also continual learning. So let me conclude my talk. This talk was given for this workshop, right? Floating-based robots and manufacturing and logistic operation, opportunities and challenges. And in my talk, I started with what kind of opportunities we had and how that shaped into our industrial robot programming, actually. So I started with hardware development and software development made us to make some first step towards the collaborative robot, right? Hardware development like lightweight robots and joint torque sensing and controllers like impedance control, compliance controls that allows to do us direct teaching. And I try to convince you how robot learning can further assist human programmer to do the robot programming, basically. And I hope I showed you some examples of that. So I hope I showed that robot learning can enhance the teaching multiple skills, conditional skills, and also continual learning. So my main take-home message would be collaborative incremental robot programming leads to active learning of hierarchical tasks and conditional tasks. So before really conclude my talk, I would like to advertise some of our recent work, especially our contributions at Humanoids conference here. So we have work on the combining task and motion planning. And we have closed-loop variable stiffness control of dynamic systems. And also we have worked on the iterative learning control of both the virtual repellent point adaptation, and the other two papers are more fitting close to the topic of this workshop. So let me give you a bit more introduction of these two works. So first work is the done work of the our master this student Felix and also Thomas. And this work is about the detecting is it the intended contact or unintended contact, but during the robot is doing some contact tasks, like robot is doing table wiping tasks, and then human is lifting something or want to change robot's positions, or is it really unintended collision? So this work will be presented in the interactive session on Wednesday. Also, we have a live Zoom session for that as well. So please come and then ask, see what we do. And we can have more interaction there. And the second paper is done by the Thomas. And this will be presented in the session of learning and AI. And the work is about the force-based robot skills. So we proposed a set of basic force-relevant robot skills like touch, press, contour, turn, push, insert, hand over, press, and slide. And we assess the understanding of these context skills from the human perspective and also robot perspective as well. And yeah, and actually the work has the intention to have this kind of outlook actually. So when human shows the, for example, wiping behavior or press and slide behavior, and human demonstrate this motion and also force profile. But as you can see, once robot is detecting, this is press and slide, then robot doesn't need to reproduce exactly same thing as what human provide, because human cannot always provide very optimal behavior neither. So you don't want to make robot to follow exactly this shaky force profile. But if you know that, this is press and slide, and then I know desired force step level, then robot can reproduce or produce the motions more optimal manner by understanding what is underlying constraints of that. So please visit us, and then let's talk more on that. So this is the end of my talk for this workshop, and I'm looking forward to have more fruitful discussion with you at the online workshop session on Monday. And thank you very much for your listening. And also I'd like to thank our collaborators, especially our team members. Yeah, thank you very much.